All right, we're back. We're doing more computer vision. It's always exciting. How's it going, everyone? So we have a logistics slide, which is probably somewhere, but let's talk logistics. You have your homework right now. You guys are working on it. There's a Google group. As far as I know, no one's posted in it yet. People are still sort of posting in Mattermost. That's fine. Wherever people want to ask questions or whatever is cool. Anyone have any questions or sort of logistical issues, anything? Seems like everyone's good. Cool. So we went through a bunch of stuff last time, so I just wanted to quickly go over the panorama stuff and then just like cover the feature stuff a little bit at the beginning of class one more time, just because we covered it all very quickly, and it's some pretty core stuff in computer vision that everyone should know about. So we talked about estimating basically transformations between images so we can stitch together these panoramas. We talked about how basically what we're going to do is set these up as linear systems of equations and then solve them either for the exact solution or for the least squares solution if they're overdetermined. We talked about why solving this equation actually minimizes this least squared error between the actual points that we want to project to and sort of their reconstruction or their projection. And we talked about basically least squares is good for a lot of things, but it doesn't deal very well with outliers. So if you have sort of one outlier in what would otherwise be a really good data set, you can kind of throw off your whole estimate if you're using least squares. And so we talked about ransack, which was basically, I mean, someone put it really simply, like, isn't this just trying a bunch of different models and seeing which one works best? Yes, that is exactly what ransack is. You just try a bunch of models. You use sort of random data to estimate each of these models, and you see how many basically inliers each of these models have. And you're sort of assuming that basically there will be a lot of inliers that all agree on what the right model should be, and all of the outliers will all disagree on what they think the right model should be. So if you have sort of a data set where there are a bunch of outliers, but they all agree on something, it's hard to even really call those outliers at that point. Maybe there are just sort of two modes in your data or something else different going on. But basically, ransack works really well when you have some noisy data, but a bunch of inliers that all kind of agree on the same model. So in this, we sort of went through this example where we estimated this line, and it worked pretty cool. And we went through sort of the algorithm. Someone have a question? Yeah, OK. Then we went through basically how ransack can work well for panoramas, and it works well even with sort of this extreme noise that we were seeing. And this is just sort of showing the inliers that our ransack algorithm found and also the outliers that it found when we're stitching together these two images. We went through basically how what we actually want isn't this affine transformation, but this homography, and how if we make this assumption about the homography that H22 is going to be equal to 1, then we can do sort of this same process where we're solving this in terms of matrix equations and basically setting up this big linear system of equations. And we also talked about how this isn't always the right thing to do because sometimes H22 can be 0, basically, and then solving it this way will kind of fall apart. But most of the time, this will work pretty well, and all we care about is that it works well when it really counts, because that's sort of how ransack works, right? We can make a bunch of errors with ransack, but as long as we get sort of one model that works well, we're going to be all right. Yeah? I'm honestly not even sure what that would correspond to. Yeah, so if H22 were 0, well, I guess you could see it, couldn't you? Because all that does is change basically the W component that gets multiplied by. So they do talk about lines at infinity occasionally in homographies, and I can't remember what the context was for this. I'll look this up on Wikipedia and get back to you. Yeah. In general, it's a pretty safe assumption to make. When you guys are doing your homeworks, basically sometimes when you call the solver to actually do basically this matrix inverse, it will sometimes just say, I can't do it. And that's because something weird has gone wrong. Maybe some of the assumptions we make are bad, or there's just something going wrong with, it's just doing sort of pretty simple Gaussian elimination, so it's not like a very smart matrix inverter. And sometimes these matrices aren't necessarily invertible. But if that happens, you can just sort of ignore it and go on to the next sample and just keep trying to estimate. And at some point, you will probably, at least for all of the images I gave you, you should be able to estimate sort of the right homographies, and they should stitch together well, et cetera. And then we talked about basically how when we actually end up stitching these panoramas together, we have some sort of weird skewing and warping happening near the edges. And the reason that that happens is basically we're taking all of these images and we're trying to stitch them all onto the same basically flat image plane. And in particular, it's sort of whatever image plane we kind of start with. So in this case, the plane that corresponds to the green image. And when we do that, basically the edges of the blue and pink image get really stretched out and kind of warped. And in particular, this kind of limits the panoramas that we can do, because as we sort of increase our field of view of the panorama, we start to sort of stretch out this image plane kind of to infinity. So you can't really get anything more than like, a little bit less than 180 degree field of view, basically. And with 180 degree field of view, you'd have sort of an infinitely large image plane, and it would be really weird to stitch together, and really bad things would happen. And in practice, it starts to break down actually pretty quickly when you're stitching these things together. So instead, what we're going to do is basically project these images onto a cylinder, and then do our stitching with those images instead, and that works out a lot better. We went over basically the equations to project these images onto a cylinder and how we would go about doing that, and how, even with just sort of this relatively minor level of warping to these images, we can actually get pretty good results where we can stitch together this really wide field of view. I think this is probably a little bit more than 180 degrees in terms of actual rotation, but I'm not totally sure. And then we talked about basically when we're doing this stitching process, we are matching together features and some sort of descriptors of places in the image. So a lot of times just kind of what we use is like pixel values. That's sort of the easiest thing to think about using. But in particular, if we're just sort of like talking about pixel values, there are a lot of issues. So one of the things we talked about a while ago was how they're sort of not rotation invariant, and that's bad. But also we talked about how they're not invariant to lighting and sort of changes in like exposure or maybe different color, sort of hue, tints, and things like that. And so we talked about a couple different possible ways that we could get features. So one was this histogram of oriented gradients, or HOG features. And this was introduced by Dalal and Triggs. And this was sort of meant to be a better image descriptor. So instead of using pixel values, we're going to use gradient information. And why this is cool is if you change sort of the exposure of an image, or if you shift around the colors a little bit, in general, you're not going to change the gradients in that image, even though you're changing the pixel values. And so all this feature is basically you're aggregating together a bunch of nearby pixels, and you're aggregating the gradient information at those pixels. So what you're going to do is compute the gradients, and then you're going to basically sort the gradients into different bins. So we have a little basically pie chart here to kind of show you what that actually means. But basically, if the gradient is pointing roughly in sort of this direction, you're going to sort it into this bin. If it's pointing roughly in kind of this direction, you're going to sort it into this bin. And then you can come up with a histogram for all of these different locations in your image. And so we're going to aggregate together basically these blocks. A lot of times people use sort of 16 by 16. And then we're going to normalize these gradient magnitudes, and that's the step that really helps with dealing with sort of exposure changes and lighting changes and things like that. So all that you're really looking at is basically the relative amount of gradient in one direction versus another direction versus another direction. And the hope is basically that even with some pretty significant changes in terms of lighting and stuff, all that really matters is what edges are present in a location, and that basically the ratios between those gradient magnitudes will stay somewhat the same and kind of be invariant to some of these lighting changes. So Dalal and Triggs use these features to basically train this SVM, this machine learning model, to recognize people in images. And basically, if you have sort of a person in an image, you can extract HOG features, which are shown sort of in the middle image, and it's kind of, you can like kind of sort of squint maybe to yourself and see that there is a person there. But when you sort of visualize these hog features based on what the SVM is seeing, based on what this machine learned model is seeing, it becomes really clear that there's sort of a person at that location in the image. So the SVM basically has these trained weights to scan over these features and look for people. And in particular, basically, you can see how, if there were some pretty significant changes in terms of like lighting or color in this image, it would still basically be extracting these same features where you have, some kind of round thing at the top and like you can kind of see like the shoulders a little bit, I guess, and then just like a lot of straight lines up and down the actual body. And this works pretty well for basically detecting people in one orientation, which is like straight up and down. And if you're like a self-driving car, this is one of the kinds of people that you definitely would want to detect. There are probably others, maybe like people on bikes and stuff. And people have extended hog features to work in more complex domains. So not just for sort of upright people, but for a bunch of different, detecting a bunch of different objects. And we'll talk about that when we get to object detection a little bit. But hog features are cool, as we said, because they're invariant to sort of changes in lighting and color. And in particular, you have a bunch of different people. They're going to be wearing different clothing. They're going to look a little bit different. But if you sort of look at their general outline, they are going to more or less look pretty similar. Or at least they're going to have hopefully a lot of similarities to each other. And hog features can kind of get at that core essence of like, what does the outline of a person look like? Or if I'm sort of looking around and I see some features, how confident can I be that that's like a person standing there? So that's cool because you can go a lot farther with these features than you can with just sort of pixel value information. No, so yeah, I guess the second image is just the actual straight up extracted hog features. And the second image is looking at the weights that this SVM has on each of these locations and on the gradients in different directions, and basically reweighting the features based on those weights. So yeah. Yeah, so the training is actually pretty easy, basically. You have a bunch of images, you extract hog features from all of them, and you have someone go through and basically mark out where all of the people are. And then you have all of these boxes that have people in them, and you also go through and find a bunch of boxes that don't have people in them, and you feed them all to this machine learning model, and you say, this box has a person, this box doesn't have a person, et cetera. And then at test time, when you're wanting to find people in new images, you basically extract features from the image and then apply your model at every location in that image. So the actual application is sort of this sliding window thing. The computer went to sleep, I think, but it'll come back at some point. Any other questions while we wait for it to reconnect? Your chance. And so we talked about, hog features, yay, that's cool. But actually, we're still not to sort of what some might think is like a perfect feature or something. And in particular, hog features are not rotation invariant. So we were talking about Harris corner detection, and it is rotation invariant. But it is not invariant to things like changes in scale. So we see at the bottom here when we're detecting corners, our corner detector will fire with sort of a corner in any orientation. But if you start to kind of zoom in on a place where there might be a corner, as you get closer and closer, those corners can start to sort of look like lines if you look just very locally, basically. And so the Harris corner detector has some issues because it's not invariant to scaling, and hog features have some issues because they're not invariant to rotation. So maybe we want some feature that could be invariant to basically all of these things and handle sort of a wider variety of changes that we might see in an image. And that's where we got to SIFT features, which are scale invariant feature transform features. I don't know. So SIFT is, I guess, people talk about SIFT features, which maybe is redundant. But anyway, SIFT features are basically a way to extract features that are invariant to changes in scale. They're also invariant to a pretty wide amount of changes in terms of rotation. They're not completely rotation invariant. And they're also invariant to sort of lighting changes and stuff. And so it actually combines together a lot of the things that we've already been talking about, basically. The first step is going to be getting this scale invariant response map. And to do that, basically, we're going to extract difference of Gaussian features at a bunch of different scales and a bunch of different values of sigma for our smoothing function. So we talked about how basically difference of Gaussians is you apply a Gaussian smoothing at a couple different values of sigma, and then you take the subtraction of those, and you get basically a response map of features in an image at a certain basically band of high frequency versus low frequency, et cetera. And so difference of Gaussian features can give you responses for where there are edges in an image. They can also give you responses for where there are corners in the image, basically areas of interesting stuff going on. And how we're going to make this scale invariant is basically resize the image to a bunch of different scales and extract these features at a bunch of different levels of resolution. And then what we're going to do is find basically local maxima, both in terms of location and in terms of scale. So for every pixel, you're going to look at, I think, 27 neighbors or 26 neighbors or something. You're going to look at the surrounding, basically, pixels in XY location, but also you're going to look a scale up and a scale down. So you want basically every strong response in your SIFT features to be strong in terms of where it is, but also in terms of at what level of resolution you're looking at. Then just for those points that you've picked out as being strong responses already in terms of this difference of Gaussian features, we're going to estimate, so everyone should be sort of familiar with this, we're going to basically estimate strong responses in terms of gradients, and then we're going to look for things that look like corners. And again, we're sort of using this structure matrix thing where we're trying to estimate basically the second eigenvalue. I don't know why people are so afraid of just calculating the second eigenvalue, but for some reason everyone just comes up with their own little way of doing this estimation. So we're still going to use basically determinant and trace information, but just a little bit different than last time. So basically all of this has been to filter out all of these pixels in this image to basically use the difference of Gaussian to find some interesting things, and now we're filtering it down a little bit more to get the actual really interesting things, which are the corners. But since we did this sort of processing where we're doing it at a bunch of different scales, we're going to get these features that we're going to detect them, if you're really zoomed out in an image or if you're really zoomed in. We're going to start getting some of this scale invariance, basically, which is cool. And then once we've found these interesting corners in the image, we're going to actually extract our feature descriptors. And this is very similar to sort of our histogram of oriented gradients. But this time, instead of basically maintaining the orientation of the gradients as whatever direction they were basically pointing in the image, we're going to normalize them based on the strongest response in terms of the gradients. And we're actually going to compute multiple descriptors at every location if there are a bunch of strong gradient responses. So we're going to look for basically the peak response of all of the gradients at some location. And then any gradient that is above 80% of that peak response, we're going to form a separate feature descriptor for that gradient. And then what we do is basically shift all of the other gradients to normalize based on which direction that peak gradient is pointing. And then we're going to calculate basically the same histogram where we're looking at a bunch of different, or at a few different patches in the image, and then aggregating all of the gradient information around that patch. And so, and the final step in this process is basically taking these feature descriptors and doing some normalization with them. And for some reason, the normalization process that people came up with was you normalize them to basically have unit magnitude or unit length, and then you clamp them so that the maximum length of one of these vectors is 0.2, and then you do the same normalization again so it has unit length. And this helps deal with sort of really extreme changes in lighting. Because again, remember, what we really care about is like, what are all of the different gradient directions and sort of their relative ratios to each other? And we sort of hope that basically by doing this normalization process, we get rid of some of the effects of like large lighting changes on how these gradients kind of relate to each other. And we talked about how these SIFT features are really good at doing some basic kind of recognition and finding some of these objects in images. So this is an example where you sort of extract SIFT features from this train and from this frog, and then you look in this more cluttered image to try to find those same objects again. And you can see that basically, I can't totally see here, but it comes up with some matches for these things. And especially if you look at the frog, which is kind of hiding behind this black box, it finds that frog even though it's like pretty significantly changed in terms of scale. And it also has a bunch of occlusion. It's sort of like behind this little, I don't even know what that is. I don't know, that little, it looks like a TV almost, but it's so small. Anyone know what that is? Oh, okay, well, a tiny little safe on top of the CDs. Anyway, it's also good at finding some of these random objects that were kind of fed into it in this more cluttered scene. So SIFT is good at sort of doing this feature extraction, finding these interesting key points, and then extracting these descriptors from them. So it's cool because it's kind of doing this whole process as part of one big algorithm. And you can think of this as sort of like we were doing Harris for key point detection and then sort of using pixel information for our descriptor. But this is kind of doing key point detection and descriptor kind of formation all at once. SIFT was for a long time sort of like the pinnacle of feature extraction. And it's still used for a lot of things because it's really fast and it still gets pretty good results. I think SIFT is patented, so people talk about it all the time, but in practice they actually use some like little minor changes to the algorithm called like SURF, or there's a few other ones. This is an example of why you shouldn't patent things, because no one will use your stuff if you do. They'll just like make some little tweaks to it and just use that instead. So we're done with all of that kind of feature stuff for now, and I'm going to turn it over to Connor, who some of you know as one of the TAs for this class. He is also a PhD student in robotics. He's published a bunch of papers in top conferences about robotics and vision and teaching robots how to see. And he will be talking to you guys about some things related to sort of images over time and also images in three-dimensional space. So optical flow and video processing and stereo vision. So I'm just going to transfer the mic over to him. You guys can chat amongst yourself.
Cool. Testing, testing. Oh, it works. Cool. Okay. Hello. For those of you who haven't met me yet, haven't come to my office hours, I'm Connor, just like Joe just said. And so today we're going to talk about optical flow. So I had a whole big, long, complicated lecture planned. We're going to go over some cool sparse algorithms and some cool dense optical flow algorithms. Looking at the time now, I don't think we're going to get to the dense optical flow algorithm. I'll still show you the demo because it's cool to watch. But the one that's the most important is the first one here. So we're going to talk about sparse optical flow, specifically the Lucas-Kanade algorithm. If you have no idea what any of those things mean, that's okay. We're going to get there. So I think the first thing that maybe most of you are wondering is what in the world is optical flow? So at its most basic, optical flow is just a measure of movement. What's moving, what's going on, what do we see? And so up until this point, we've largely looked at just static images. But if we're measuring movement, that requires some notion of time. So if we've got some notion of time, we need multiple images. So here we're going to look at sequence of images, aka videos. So here there's two images taken in subsequent points in time. And you can see in these images there is some movement. Our bender robot is going from the left side of the image to the right side of the image. And so there's movement in this image. And in this case, our movement is caused by an object in the image moving. But movement in an image doesn't have to only be caused by things that we're looking at moving. It can also be caused by what we're using to do the looking, our camera moving. So our camera could be panning left or right. Our camera could be moving forwards or backwards. So there are lots of things that can cause movement over time in our images. And I found this cool video on YouTube that I'm going to show you. I'll show you a demo, live demo later, but we'll just do the video for now. And so what you can see here in this video is this guy is playing, would this be considered Pong? Using optical flow. You can see here's the flow, all the flow vectors, and it's kind of, they show where everything is moving. So you can see like when his head moves left and right or when his hands move, all these little vectors light up. Challenge for this class, implement this algorithm. Okay, so that's what optical flow is. At its most basic, it's just a measure of what's moving around. So when we're talking about moving, we're talking about over time, so things like videos. So now we also want to know, why would we want optical flow? This will go to the next slide. There we go. Okay, why would we want to have optical flow? Why would we want to know what's moving around? So we get these nice motion estimates. We have a pair of images here taken at subsequent points in time, and we can estimate kind of where everything is moving around in the image. And we can use this motion estimate to do things like object tracking. So if we have a stationary camera, we can track where all these cars are moving to, or whatever. If we have a robot that's moving around, we can use it to do visual odometry. Basically, our camera is fixed to our robot, and our robot's moving, so we can, based on where all the fixed things in the environment are, we can figure out how our robot is moving. There's actually, I forgot to put a picture of it, but there's a cool work out of CMU from a couple years ago where they used optical flow to detect fluids moving, like water, soda, beans, whatever kind of flowing in an image, and it was pretty cool. So you can use optical flow to do lots of interesting things. So how do we actually find the flow in an image? Well, Joe just got done telling us all about feature matching. So we just learned about these cool features, finding features, hog features, SIFT features, SIRF features, whatever kind of features you want, corner features, cool features. And we also just learned about how to do panorama stitching, which is what you're doing for the homework. That's due next week, I think. So it seems like conceptually, panorama stitching and optical flow should be pretty similar. In panorama stitching, we have two images taken next to each other in space, and we're trying to figure out basically where the features align between the two images. In optical flow, we have two images taken next to each other, but in time this time, and we're trying to figure out, again, which things line up to which things. So it would seem like the sort of obvious way to do optical flow, if we want to find where things are moving, would be just to sort of apply our feature matching techniques, but instead of doing it to images next to each other, we do it to images next to each other in time. So if we go back to our original image, we could just do something like this, where we find some features in the first image, find some features in the second image, and then we can just line them up. Cool. Line them up, match the features, and we can tell kind of where everything moves. We can tell where Bender's antenna has moved, where his arms have moved in that image. Great, great job. Solved it. Good, you can go home now. So in practice, it turns out this doesn't actually work out that well. Does anyone have some ideas why this might not work so well? Like what kind of disadvantages doing like a feature matching approach? Yes? Right, so he's saying if something shifts position, like it turns in an image, you see it kind of a different side of it, then it'll be difficult to follow it. Okay, great. So he said basically if you have more of your image, like the background is not moving, and only a small part of the image is actually moving, you'll actually detect the moving parts of your image as outliers. Anything else? Cool. Okay. Those are great things. That's definitely one thing. Another thing is these tend to be sparse, so they only give you very limited movement, you only get movements at the features. Sometimes your feature alignment is not always exact. So what I mean by that is, well, a lot of times we can find very similar features from one image to the next. But for example, if I don't actually have a picture of benders slightly turned, but if you imagine benders slightly turns, then you're going to get different features. Which a lot of times this feature alignment isn't usually a huge problem if you're doing something like panorama stitching, because if you imagine that we found Bender's antenna here like that in one image, and on the second image we find Bender's antenna but slightly lower, then that small error would end up averaging out, because what we care about in panorama stitching is just the overall transformation between the two images. But in optical flow, we could have different parts of the images moving in different ways, so we have a lot more parameters we're trying to estimate here. So for example, Bender's arms could be moving differently than Bender's head moves. And so in that case, you get a lot of this these little inaccuracies add up a lot. And so it leads to kind of low accuracy. Some advantages of this, though, and we just talked about this a little bit, but it does tend to be more scale and rotation invariant than some other optical flow methods. And it is kind of lighting invariant if you do like SIFT features, and that can tend to be more lighting invariant. And it also can tend to handle large movements. So if Bender moves entirely from the left side of the image to entirely the right side of the image, you can detect that with feature matching. But overall, it doesn't really tend to work very well for optical flow. Now, I should add a caveat here. There are like 1.5 billion methods for optical flow. If you Google optical flow review, you will find like hundreds and hundreds of papers that do hundreds and hundreds of methods. Everyone has tried every possible method. So feature matching is a thing that people do. It just tends to be a little bit harder to get it to work in practice. So what should we do instead? Let me point out an observation here that just kind of fundamental to how movement works. It's not a huge observation, but it's important. So okay, if we imagine we have here 4 images in a row taken in time, and we've got our little cylinder, and that cylinder is moving to the right. Now, if we want to observe the center pixel, let's say we're observing the brightness of the center pixel in every image. So let's observe the brightness of that center pixel. You'll notice that it gets brighter over time because as the object is moving, we're looking at a brighter side of the image, a brighter side of the object. So if we take this brightness and we plot it, so here our x-axis is time, and our y-axis is the brightness of our center pixel, or we'll call it the observation pixel, then we get this nice plot that looks like that. And we can describe this with a function. So our function here is what is the brightness of our observation pixel at some point in time. Okay, so now let's go back and look at just that first image again. So here, in this example, we are holding our observation pixel in place, so we're holding it in the center of the image, and our object is moving underneath it. We've got this motion in time. But what if we did the opposite? What if we kept our object in place and we moved our observation pixel? So we start our observation pixel in the center, but here let's move it in the opposite direction as the object. So we're going to move it back to the left, and then we're going to get those observations again. So you can see here we're going kind of in the opposite way. So it starts out lighter, it goes darker. If we plot these again, and we're going to plot them here, plotting them just kind of in reverse order, we get another nice line that we can fit another function to. And this function is basically, as we go left in the image, the observation pixel gets brighter. And you'll notice that these look the same. So the insight here is that moving the object to the right is the same as moving the observation pixel to the left. And this is not some fundamental insight. It's kind of like, well, duh, no crap, of course that's true. But it's very important to understanding how these optical flow algorithms work. So basically, a movement in time, our object moving in time, is the same as moving our observation in space. So we're going to look at the Lucas and Kanade optical flow algorithm, where they basically ask, can we use this relationship to compute optical flow, to compute the movement of things in the image? And that was published in a paper. This paper, you do not need to read this paper or anything, but if you are super curious, you can if you'd like, called An Image Registration Technique with an Application to Stereo Vision. Notice it's published in 1981, so it's almost 40 years old at this point, which is pretty old by computer vision standards. But it is sort of the classic optical flow algorithm. And you guys should make sure to pay extra close attention, because for the next homework, which I think is going to come out next week, because we're a little bit shifted off schedule, you're going to be implementing this algorithm for the homework. And I also encourage you to stop me and ask questions if anything's not clear. Okay, So what they did in this algorithm is basically, can we take that relationship we just talked about and put that in equation form? So here, if we're assuming our movement is represented by delta p, and our movement is over some small period of time, delta t, then we can put that in an equation that looks like this, where again, our f is a function that says, okay, at this pixel, at this point in time, this is the brightness of that pixel. So here what we're saying is the brightness of our pixel from our moving in the opposite direction of our object from our observation point in the first image should be the same as the brightness at our observation pixel in the second image. This is that relationship. If we move our observation in the opposite direction as the object, then that should be the same as if we just move the object, which the object moves forward in time. So these two things should be the same. Okay, so that's our observation point. Just to keeping the notation straight here, we're going to use p as the observation point. The math is going to get a little bit finicky here, so again, encourage you to stop me and ask questions. That's our movement, so this is how much that's moving, delta p. That's basically just t means the first image, t plus delta t just means our second image, and this is the brightness. Okay, so basically we want this function, but this function is going to be super duper really complicated. So we can't know it exactly. But what Lucas and Kanade did is they basically said, let's approximate this with a first order Taylor expansion. And I know what you're thinking. You're thinking, I haven't taken calculus since freshman year. I don't remember what that means. Great. It's a little pet peeve of mine when people throw in jargon into presentations and then don't explain it. So it's like you miss what they said, and it's like, oh, I completely forgot what that was. So for those of you who have forgotten what Taylor expansion is, here's the quick and dirty Taylor expansion. It's just approximating a complex function with an nth order polynomial, which is that's so easy to understand. Sarcasm. Okay, so it's basically something like this, where you're just saying our function that we don't know what it really is, we're just summing over a bunch of weights times x to the whatever power. So for first order, that literally just means this. So some function or some weight times x to the first plus some weight times x to the 0, which literally boils down to our equation for a line. So when I say we're approximating this with a first order Taylor expansion, that's a really fancy way of saying we're pretending it's a line. So that looks like this. Here's our super complicated function that we're trying to approximate. Here's our line. The point about Taylor expansions is that they always set it up such that whatever point we care about, this x point, and maybe that's the point we care about, that our approximate solution always equals our actual equation at that x point. So you can see here it's attempting to match it around x. What this means in practice is basically our approximate function here is really only good around this point, and when you get further away, it kind of sucks. Okay, so we're approximating this with the first order Taylor expansion. That basically means we can replace this whole function here with our equation for a line. So remember, mx plus b. Here's our x, p minus delta p. So we're just going to say m times b, p minus delta p plus b is approximately equal, because we're using a Taylor expansion, to the brightness in the second image. Okay, and we just multiply this out, and we get this nice, fun little equation there. And I ran out of room on the slides, so we're starting at the top of another slide. These slides will all be available online for you to look at, but do feel free to ask questions. Okay, so here's our equation. Just for the heck of it, because we can, let's subtract off our brightness of our observation pixel in the first image. So here we're going to subtract minus fp at t off of both sides. So this is, again, still equivalent since we're subtracting the same amount from both sides. And the reason we do this is because if you remember, when we were doing the Taylor expansion, we set it up such that at the point we care about, the point we're expanding about, that is exactly equal to our approximate solution. So we can just plug this back in here for this now as well. So if we plug this back in, right there, so we take this equation, we plug it in there, what we get is plugging in here cancels out our MP term and our B term, because it has this minus sign. Those terms cancel out, and we're left with this. So we basically get minus m times delta p approximately equals this stuff. So what this means, intuitively speaking, is some m times our movement equals the change in brightness from our first image to our second image. at our observation pixel, the pixel we care about, P. Okay, so these we know. We can just look at the image directly and figure out these values. This is what we want to know. So we want to solve for delta P. We want to figure out what that movement is. So what is this? We have just this random m term that doesn't really mean anything. We just like said, okay, mx plus b. What is m? What's going on with m? So if we look back at when we did our Taylor expansion, you'll notice that this here, our line here is tangential to the slope of our function. So basically that means that basically means it is equal to the derivative. Again, we're calling that fun calculus, or also known as the gradients. And we already know how to do gradients. You guys did gradients like a week and a half ago, I think, and you did it on the last homework. So if you recall, we already learned how to do gradients. This isn't the exact solution for the gradient, but this is an approximate solution. But we already learned how to approximate the gradients. So why don't we just take those gradients that we already know how to do, and let's just plug those in here for m. So here we have, I'll call this the gradient P matrix, which is, again, just going to be a diagonal matrix with our x gradient and our y gradient along the diagonal. Okay, so that ends up looking like this. So here's our equation now. This is getting a little bit wonky, so let's actually look at what the actual x and y's look like in here. So if we actually multiply this out and get rid of the vector notation. Oh, you have a question?
Yeah, just to make sure t is
Yeah, I put it as a parameter. I'm kind of cheating a little bit. It's not really a parameter. It's basically a fun, fancy shorthand way of saying second image, first image. Actually, a lot of people, if you read the papers that people use, they'll usually write t as a subscript right here to indicate first or second image. That might have been a little bit cleaner to do it that way. Okay, so let's drop this vector notation. And if we kind of just multiply it out, so our delta p here is, again, just going to be our delta x and our delta y. And if you remember our dp matrix, that was just that diagonal matrix. So when we multiply it out, we get our gradient, our x gradient, times how much we're moving in the x direction, plus our y gradient times how much we're moving in the y direction, should equal the change in brightness. All right, now in the literature, usually the notation is a little bit different, and this notation is kind of hard to read. So we're going to clean this up a little bit and kind of use the more standard notation. So here what we're doing is we're going to replace delta x and delta y with u and v. So usually when people refer to the change in x and the change in y, they use u and v because they really like those letters for some reason. We're going to replace here like this super complicated looking functions that are getting really messy with, this literally means just go to the image and look up the brightness at pixel x and y. And this is the first image and the second image. Oh, that's the other thing. Good pointing that out, though. Not that. I flipped the negative sign. Secretly, while you weren't looking, I moved the negative sign. I got sick of it being over here. So yeah, we're just going to flip the negative sign over to there. Just multiply everything by -1. Okay, so hopefully, this makes sense. So we got this nice equation here that relates how we're moving, the movement of the image, u and v, to the change in brightness and our gradients. Okay, so we know how to compute our gradients, or at least our approximate gradients, using our convolution filters that we already learned about. And we know how to get these. We can just literally look at the image directly to get these values. So all we want to do is just solve for u and v, and then we've got it. We've got the motion. There's a little bit of a problem with this, though. If you notice, we have one equation and two unknowns. And this problem is underspecified, which is literally impossible to solve. So there are lots and lots of different u's and v's that could all solve this problem. So this is a little bit of a roadblock here. So let's back up and kind of figure out. So we just went through all of this like super complicated math, trying to figure out how these equations relate. But let's back up and kind of get an intuitive understanding of what this whole equation really means. So here's our equation. This is our equation that relates our movement in space with our movement in time. So what is this like? What does this mean? What's going on here? Okay, so if we go back to our original two images, or if we go back to our original images here, if you imagine here's our two images, t and t plus delta t, so first image, second image. What's going on here, what this equation is really computing is saying, okay, first take our first image and compute our x and y gradients, just like we already did. And then, these x and y gradients basically give us what is the brightness per x pixel to the right, how does the brightness change per x pixel to the right, how does the brightness change per y pixel down. And then we multiply that by how many actual x pixels we're going to move to the right, or how many y pixels we're going to move down, and then we just add those together. And what we're saying is the change in brightness as predicted by our gradients here, our gradients in our motion, should be the same change in brightness that we actually see in time. But this problem is underspecified. Like I said, there are lots of potential movements that could all give you the same result. So we can't actually just solve for it. So the idea that Lucas and Kanade had all the way back in the 80s was, what if we assume that neighbors all move together? So maybe a little small neighborhood of pixels, and they all move in the same direction. So here, instead of just having a single observation pixel, let's have a little 3x3 grid, or a little 3x3 image patch. So we're going to say all of these pixels are all moving together. What we get then is, instead of having one equation and two unknowns, we actually get 9 equations and 2 unknowns. So we have all 9, so 3x3, there are 9 pixels. So we look at all 9 pixels, they all have the same u and v, and they should all satisfy these equations. Okay, so this seems overspecified. So now we have big red text. Now we have more equations than we have unknowns. So now we have the opposite problem. So Joe just talked about, earlier in this lecture, and I think he talked about it last time too, using least squares. So in this kind of case, when it's overspecified, what people usually do is they'll use a least squares solution. And here, because it's only a 3x3 image, I don't think we're that worried about outliers. So least squares is okay here. So we want to set this problem up as a least squares problem. Then let's just rewrite these 9 equations as one equation, and we're going to do that using matrix notation. So here we're just going to say this S matrix, and this S matrix is going to be our x and y gradients for each of our 9 pixels. Our delta p, again, is just our u and v in a vector. And then our T matrix over here is just the change in brightness for each of our 9 pixels. And it's actually just a vector, not actually a matrix. And so we can write our 9 equations, we can now write them as just one big equation, S times delta P equals T. And then we can do the least squares solution, which you guys have seen least squares already, and that ends up coming out to this. So delta P is equal to S transpose S inverse times S transpose times T. So you can solve for the motion directly. But there's a little bit of a problem. If you look here, you'll notice this little inverse sign here. What happens if this is not invertible? Then if that's not invertible, then we just can't solve it. What does that mean? What does that mean if it's not invertible? That means, for example, there's no structure around x and y. It's a bad feature. So basically that means if you imagine, for example, you're looking at a flat wall. If you're looking at a flat wall, you can't really tell if it's moving or not because it looks the same if it moves or if it stays in the same place. So what we want to be able to do then is, before we get to this point, before we actually try to compute the flow and we get an uninvertible matrix, we want to test to see if it's invertible. So we want to test this equation here. We want to test this S transpose S to see if that's invertible. And if it is invertible, great, we can compute flow. If it's not invertible, we're out of luck. Okay, so we know that S transpose S is symmetric. If you'd like to actually work that out on your own, feel free to, but it's symmetric, take my word for it. Which means we can decompose it as this kind of a matrix with its eigenvalues down the diagonal, and then we can make it, we can solve the characteristic equation to basically get this. So what we get is the determinant of this matrix here is equal to 0. And then when you actually multiply out the determinant values here, which is just this value times this value minus this value times this value, what you get as a result is a quadratic equation, and we can just solve quadratic equations. Quadratic equations usually have 2 solutions, so that's where you get lambda 1 and lambda 2. So you can just solve the quadratic equation to get the two solutions. And if either of them are less than 0, which means they're imaginary, then it's not invertible. There's no solution. So we just went through this whole thing about how sometimes, yes? Potentially. Yeah, I mean, it's just basically if that's not invertible. So any test for invertibility you could use. I was just, since you guys have to actually implement this, I wanted to give you like very clear equations so you can do it. Okay, so I just talked about how we can compute optical flow for some x and y location, some point. But then there's also going to be some points where this S transpose S is an invertible, and that basically means we can't compute optical flow. So how do we actually pick x and y locations to compute optical flow? So I want to ask you guys, what do you think about this location? Is this going to give us a lot of good optical flow? See some no's. Anyone want to venture a guess why? Exactly. So we couldn't tell. So if this box moved left or right, in this little image patch, it's going to look exactly the same. So we can't tell at all. If you think about it from an intuitive level, we can't tell at all that if it's moving. So this is a really bad feature to compute gradients at, or compute flow at. What about this one? What do you guys think of this one? How is this? Mediocre. Better, mediocre. Yes? Nailed it, exactly. So same, kind of half the same issue. If we move left or right, we can see that this edge is moving. But if we move up and down, we can't tell. We can't tell the difference between moving up and down and not moving at all. Okay, one more, and I can guess you guys probably can figure this out. Is this a good feature? Okay, yes, it is. We've got X and Y movement. So we literally just learned about how to do corner detection. So what makes a good feature? Corners. Corners are great features. They give us lots and lots of gradients. So and you guys already know how to do corner detection. So when picking features to do optical flow, at least for this specific algorithm, the Lucas-Kanade algorithm, which you don't need to remember that name, but picking features for this algorithm, you generally want to pick corners because they give you good X and Y gradients. Okay, I have a demo that I'm going to show you guys, but do we have any questions in the meantime? Is this clear as mud? Where did I put that? It's over here. Okay, cool. Let's see if this works. It might be a little dark. So I'm going to show you a demo of the, it's working. Okay. Cool. It's a little dark, but you can see here what's happening is, see all the little lines? It's detecting motion. So basically what's happening is you can see it's finding all the relevant features, or all good places to detect features, which not all of them are really that good. And then you can see it's detecting the motion. Okay. Does anyone want to come up here and actually be a guinea pig? It's okay if you don't want to. Okay, all right, let's get back to it. Okay, so, all right, that's the demo. Okay, so we just went through this algorithm that basically uses the change in brightness in an image and the gradients to figure out how things are moving, but of course it's not going to be a perfect algorithm. In fact, this one specifically has a lot of drawbacks. Do you guys have any ideas, kind of like intuitive high-level ideas, like when would this algorithm fail? What is it not good at? Yep, that's good, yep. So he said very fast motion. Any other ideas? Yep, so he said rotation, so it's not terribly great at rotations. In the back. Yes, that's really good. If an object becomes obstructed, then you can't do motion for it because you can't see it anymore. There's actually a really cool paper by a fellow grad student of mine where he trained a deep neural network to handle obstruction, like objects moving behind obstructions and still being able to track them, but outside the scope of this lecture. Okay, so you guys mentioned a lot of them, like large movements. Others of them are like lighting changes. So again, the whole thing is dependent on the brightness of the image. So if your lighting changes a lot, then it's going to either see motion that isn't there or not see motion that is there. Also things like specularities, where you have these like bright spots that are really hard to see the brightness, don't tend to work so well. If there are no good features in your image, if you're just staring at a blank wall, which I'm not sure why you're taking a video of a blank wall, but whatever, no judgment. That's not really going to give you great features. There's also something fun called the aperture problem. Let's look at the aperture problem a little bit closer. And you guys kind of picked up on this a little bit. Okay, so the aperture problem is, let's imagine we've got a line and it's moving up and to the right. Now, if our neighborhood looks like this, then what our neighborhood sees is this. So our neighborhood, even though our line is moving up and to the right, our neighborhood only sees movement to the right because it can't see the ends of the line. So that's one issue. The other issue this brings up is the barber pole illusion. Now, for those of you not familiar with the barber pole, which most of you probably are, but just a refresher, this is a barber pole. It's just a cylinder with slanted lines painted on it, and it spins in place. So the actual movement that's going on here is movement to the right. There's no vertical movement at all. It's all movement to the right. But if we put our neighborhood over here, what our neighborhood sees is movement up and to the right. So again, it's tricked by the fact that it has a very, very small aperture, so it can't actually see all of the movement in the image. Okay. Oh, these slides are a little bit off. I made them a few days ago before the homework got shifted. So the homework doesn't actually come out tomorrow. Ignore that. Homework's going to come out next week. You're going to implement the focus of this homework will be to implement this algorithm I just went over. Yeah, not tomorrow. And not doing a week from today. Sorry. Ignore those dates. They have changed. The top line is wrong. The second line is correct. So for the first part, you'll just implement this algorithm that I just described here. Hopefully there's enough info in those slides. And if you have any questions, feel free to ask me now over Mattermost or whatever. And then I also want you guys to come up with a minor way to improve it. And I mean minor, not, you don't need to like break the bank or anything. Just like a small improvement. Kind of, we talked about a lot of the drawbacks of this algorithm. So coming up with ways of just like how to make it slightly better. And this is not a big thing, just a small implementation of something and then kind of write it up like, I tried this is how it worked. I'll give you a couple of examples of improvements that lots of people have come up with over the years and that have been actually integrated into like the standard LK optical flow algorithms. So the first one is iterative LK. So if we go back, if this is our equation, and if we compute our LK from our equations, then what we can do, we can actually propagate forward our estimate of our change, of how we actually think everything's moving, and then we can recompute it again. So because we're using that Taylor expansion to approximate the gradients and the change in brightness, then we're going to have some inexactness. So if what we do then is we just compute the first optical flow, and then we use that optical flow to then recompute optical flow again, and we can just keep iterating, propping it forward, keep iterating and re-estimating however many iterations you want to iterate to make it better and better. So that's one simple minor improvement that people have come up with that tends to work pretty well. Another one that people do, and Joe just talked about this a little bit when he was doing the direction of gradient features, is image pyramids. So that's literally we have our two images like this, but then we rescale it to lots of different sizes. So original size, smallest size, and we do that for each of our images. And we can just compute our optical flow between every pair of images of the same size, upsample as we go back down the pyramid, and combine them together. So that's another like minor improvement that people have come up with. Okay, cool. Any questions so far? Yes. I think the main test will be just pairs of images, because that'll be a little bit easier. Joe was talking about he thought he had some code so he could do from a webcam, so you could like see it, which would be cool. I don't think we'll make you open up videos. That'll be a little bit complicated. Although it'll be cool if you want to submit one. Any other questions? Yes. Yeah. So doing like it's usually some sort of a grid. But you could. I can't think of anyone off the top of my head who's done anything other than like a 3x3, 5x5, 7x7, something like that. That's a good idea. You should try that. Instead of picking just a naive 3x3 neighborhood, you could try and say, I know that here are 5 features all next to each other, and they're probably going to move, since they're on the same line, they're probably going to move in the same direction, so maybe use that as the neighborhood. That would be a cool improvement. You should do that. Any other questions? Okay. So we've got a little bit of time left. I think we might actually get to the dense optical flow. So the algorithm we just talked about is usually used for sparse optical flows. The demo I showed you just had a bunch of key feature points that you picked, and then you sort of tracking them from one image to the next. But this presents sort of a little bit of a problem. I said before, one of the issues with feature matching is it's sparse. This algorithm doesn't really fix that issue. It's also sparse, so not a great addition. So the thing about sparse, we can only compute flow for specific features. But if we want dense optical flow, we want to know where every single pixel in that image is going. We can compute the flow for all the pixels. And this algorithm doesn't tend to work very well for dense. Technically, you could take this algorithm and you could just apply it to every pixel. But the problem is you're going to get that matrix is not going to be invertible in a lot of those cases. And so you're going to get, like, you can't just compute the flow. So in practice, it doesn't tend to work very well for dense optical flow. So we want to do dense flow. So Lucas Kanai is technically dense. Is there a dense way to do it? Yes, there is. So this guy named Gunnar Farnbeck, I probably just mispronounced his name because he's got those nice umlauts, came up with this paper called Two-Frame Motion Estimation based on polynomial expansion. That's a fun saying, back in 2003. And this is the algorithm that's commonly used if you want to do dense optical flow because it does it a little bit better. So we'll go over, we'll kind of go quickly over this. You don't actually need to implement this on your own, so we're just going to go over to high level. And if you want more details, you can ask offline. So we go back to our fun equation that looks like this. In Lucas and Kanade, that's the one we just talked about. That's usually called the sparse optical flow algorithm. We just approximated this side of the equation with a first-order Taylor expansion, fancy way of saying we pretended it was a line. What Farnbeck said is instead, let's approximate it with a second-order Taylor expansion. So instead, let's pretend it's a quadratic equation. So that looks something like this. Here was our expansion for a line, or our expansion for first order, just a line. So our expansion for second order is just a parabola, which remember our equation for a parabola, ax squared plus bx plus c. So now instead of pretending it's a line, we're going to pretend it's a parabola. And parabola is going to approximate our function a little bit better, usually a little bit better. And if we write this as using vector notation, so if our x isn't a scalar, it's a vector, so it's a u and a v, then we just write it like this. Okay, so we're approximating this with second order, so if we actually just kind of multiply that out, we get something super complicated that looks like this, and this is a complete mess. And if you can understand this just looking at it after 10 seconds, that is fantastic. This took me a while, just like, look at all these numbers everywhere, it's a mess. So let's point out a little bit of what's going on here. So here are our polynomial parameters from the first image. Here's our A, here's our B, here's our T, or C, sorry, and the T just means first image. And we're actually going to apply this second order Taylor expansion to the second image too. And in the previous case, we didn't, we just applied it to the left side of this equation. We're going to apply it to the right side too. So here's our second image parameters, A, B, and C. And if we multiply these out, it gets even worse. So here, let's just distribute everything out, and it's just become this complete chaotic mess of an equation. If you guys want to come back and look at these slides to like understand what's going on here at some point in the future, feel free. I'm just going to skip over this and say basically, it comes down to we can align the terms on each side to each other. So we can basically say this term, we can set this term and this term equal. So these are the squared terms of our equation. of our two sides. So if we set them equal, we get that our A matrix in the first image should be equal to our A matrix in the second image. And we can do the same thing here. We can say, let's set this equal to this, and we get this equation here. And we can do the same thing with the last stuff, set them equal. We don't actually care about this one at all, so you can ignore that. What we care about is this one in the middle. So that's the one in the middle, where we basically say our B parameter in our second image is equal to our B parameter in our first image minus 2 times A delta P. And so the nice thing about this is this gives us a really clean equation to try and solve for our delta P, our motion that we care about. If we want to solve for delta P, we get this. Cool. And the nice thing is A, B, and C can be solved pointwise using least squares over a small neighborhood. So that basically just means if we put a little neighborhood around every pixel, we can use, so like this, we can use least squares to just solve for A, B, and C. Yeah, so this is literally just quadratic regression. I'm not going to go into the details of this because we don't really have time for it, but you can say we could just estimate these in both images independently. Okay, but when we come back to our equation we're trying to solve, so we know how to compute A, B, and C on both sides of that equation. But we get the same problem as before, that we have this minus 1. What if that's not invertible? What if our features suck? So Farnback looked at this and said, well, let's come at this a different way. Let's not invert this and see if we can do this a little bit better. So let's try a different approach. So here instead, what we're going to do is we're going to put this A and delta P on the same side, and then we're going to have the rest of the stuff on the other side. And if you remember from however many slides ago, we said that this is equal to this, so our A's from both sides, from the first frame and the second frame are the same. In reality, it's usually the case that they're not equal because, again, we're estimating things. So what people do to get around the fact that they're not equal is they just average them together, which I'm sure is a great solution. It works in practice. Okay, so we're going to drop that T from the A. So we're just going to say this A matrix is just the average of the one from the first frame and the second frame. And we can replace this. So they replace this on this side with just the parameter delta B, because the math is going to get a little bit hairy here in a couple slides. So to make it easier, we're just going to say delta B, so it's kind of the change in B's, is going to be equal to this. So we're going to replace that with delta B. So now we have this equation, and we want to know delta P. We can estimate delta B and A from our images. We want to know delta P. So if we do the thing that the previous algorithm did, the Lucas-Canade algorithm, okay, well, let's just assume that the neighbors move together. Then what we have is for our whole neighborhood, however many neighbors we decide to have, this equation must hold true, and the delta P is going to be the same for everyone in our neighborhood. And we can just apply least squares like that. This W here is Gaussian weight. So basically, when we're looking at difference between LK and this algorithm, is that this algorithm wants to look at the neighbors in the center of our neighborhood more than the neighbors on the edge. So this is usually just a Gaussian weight. Basically says we care more about the neighbors in the middle of the neighborhood to be correct than we care about the edges. Okay, so there's still a problem with this though, is that we're still assuming delta P is constant over the whole neighborhood, but in practice, that's not really true. So we want, the whole point of this algorithm is to be much more exact than the LK algorithm is. The LK algorithm is very fast, but it's also very inexact. So this algorithm wants to be much more exact, much more correct. And to do that, they want to relax this constraint. So instead of assuming that delta P is constant for the whole neighborhood, what we're going to assume is instead delta P is just an affine function or an affine transformation in the neighborhood. So each one has its own delta P, but they're all related by some affine transformation. Which if we want to write that as an equation, that means it'll look like this. And so we can decompose this into a matrix and a vector. So the matrix here is just going to be our x and y parameters. This is literally very similar to that equation Joe just had up at the beginning of the lecture today, or very, very similar to that matrix. And then we've got our parameter matrix just like this, or vector actually. And so once again, we can just plug this back into our previous equation like that. And now all we have to do is solve for D, which it becomes this massive mess of a thing that looks completely just monstrous. But that is our solution for D. And once we solve for D, we can just plug it back in, multiply it by S, and now we've got our delta P's for all of our pixels, and it's great. Okay, but we still have the same inverse problem as before right here. See, there's that inverse function. But in practice, that tends to be less of an issue. Because they're using the second order polynomial and because they're decomposing it in this way, having that is not as big a deal. Okay, I have a demo for this, but before I do that, do we have any questions? That was a lot of math, very fast. Don't worry if you didn't get all the details. Just understand at the high level that what's going on is they're sort of approximating the first and second images with quadratic equations, and then they're trying to basically equate them and solve it. Okay, demo time. All right. All right. So this is a dense optical flow algorithm. I'm only plotting the flow about every 15 pixels, but it's computing the flow for every single pixel. So you can see as I move, it's not just picking the corners of me here. It's actually picking, it can do the whole thing. This algorithm is, if you notice though, it's quite a bit slower. See how much it's lagging compared to the other one? The other one before, remember, it was very fast, real time, but look how much this is lagging. If I go quickly, so much lag. I'm downsampling this image to make it faster, and it's still slower than the other one. And that is the drawback to this algorithm, is it is much, much slower. It's much more exact, so we get flow over the whole image, but it's also much, much slower. Okay, cool. I think that is actually all I have for you guys. So do we have any questions? Question? In that case, it was just magnitude. Red was bigger magnitude. Yeah. Yeah, so you're saying basically ignore the ones that aren't moving? Yeah. Yeah, you could definitely do that. I don't think they were doing that in this one, but it's definitely a thing people could do.